We're always hearing in the news about crises and negotiations that drag on for decades because a country is trying to build a nuclear bomb. And, of course, Iran is the prime example of this. Since the 1990s, we've been hearing every so often that Iran is close to possessing a nuclear weapon and that they've already enriched uranium to a high level, over 60%. But at the same time, they still haven't managed to build a nuclear bomb. This makes us ask ourselves an obvious question. Why is this taking so many years? Why can't a country with an unlimited budget, top-tier scientists, and natural resources build a nuclear weapon in a few months or even a few years? And what's the secret behind that strange term we always hear, uranium enrichment? What is this enrichment process, and why does it take so long? Welcome to Midnight Questions. But before we begin, if you're new to the channel, don't forget to subscribe and turn on notifications so you get our videos as soon as they're released. The basic idea behind manufacturing nuclear weapons relies on releasing a massive amount of energy from the very core of the atom. And to get to that atom and have it ready for fission and generate that terrifying explosion, we need a specific material with very rare properties. That material is uranium. By the way, uranium isn't a rare substance at all. It is found almost everywhere on Earth. Most rocks and riverbeds and seabeds contain uranium. That is why raw uranium is mined just like ordinary copper and iron. The rock containing it is broken up and ground until it becomes a fine powder, and then chemicals are added to extract the uranium and separate it from the other rocks we don't want. The final product is a yellow substance called yellow cake. But the problem is that the uranium we extract from the ground isn't the kind that can be fissioned to produce energy. The issue isn't really with extraction, but with processing. The uranium that comes out in the yellow cake isn't a single isotope. It's a mixture of chemical isotopes. The first isotope is uranium-238, and the second is uranium-235. Uranium-238 is a heavy, stable isotope that is difficult to split or cause a chain reaction. In short, it's useless for making a nuclear bomb. As for uranium-235, it's the lighter isotope that's fissile, and it's what all countries are after for nuclear weapons or even for power plants. But the problem is that uranium-238 makes up about 99.3% of the total mixture, and the 235 they want is only 0.7%, less than 1% of the ore. And the challenge doesn't stop there. Sure, we could extract massive quantities and take that minority percentage, which would still be a large amount, but the real challenge is separating these two isotopes from each other. We're not separating two different substances here, like salt and sugar or water and oil. We're literally trying to separate the same substance from itself, because the isotopes are identical in every way, same shape, color, and chemical properties, and it's impossible to tell them apart. The only difference between them is their mass, which is infinitesimally of the atoms themselves. Even the weight difference isn't significant. The mass difference between them is less than 1.5%, and this is the only method we use to separate them. This separation process takes a very long time, and it's the reason why uranium enrichment takes years. To separate the uranium isotopes from one another, they use centrifugation, a method that separates materials each other through rapid rotation. It's similar to the concept of a washing machine during the spin cycle. It spins at high speed, so the water flies out and the clothes remain in the center. However, the problem with applying centrifugation to uranium is that uranium particles are solid. When placed in a centrifuge, they will clump together and stick to each other and won't move. And even if these particles were converted into a liquid state, turbulence would occur and the liquid particles would mix with each other, and the separation process would remain ineffective. Therefore, the optimal solution is to first convert the uranium into a gas. So the first step in the separation process is to change the state of the material itself. The yellow cake undergoes a series of complex chemical reactions until we obtain a gas called uranium hexafluoride. and this gas is the magic key to the enrichment process. But at the same time, a chemical nightmare for anyone handling it, because it is a highly toxic and fiercely corrosive substance, meaning if it touches any metal, it corrodes it immediately. That's why handling this gas is a major undertaking. It requires a strict safety protocol. First, a complete network of pipes, pumps, and valves must be installed, all made from special corrosion-resistant alloys. Once the gas is ready, it enters the centrifuge stage to separate the isotopes. After converting the uranium into gas, we feed it into prepared pipes. It enters long cylinders that start spinning at insane speeds, reaching 1,000 revolutions per minute, meaning about 3 times the speed of sound. So we can exploit the slight weight difference we talked about between 238 and 235. When the cylinders spin at these tremendous speeds, the uranium-238 sticks to the cylinder wall, and the 235 stays in the center. Done? No, not yet. The uranium-235 in the center isn't pure either. It still contains some 238. This whole process increases the concentration of 235 in the ore from 1% to 2%. But then the gas on the edges is extracted and either discarded or recycled, and the gas in the center, which now has a slightly higher percentage of 235, goes back into the centrifuge, and we repeat the process thousands of times without stopping. There's a huge network of centrifuges connected to each other, and each one increases the percentage of uranium by a few percentage points and transfers it to the next machine. It's a slow, difficult, dangerous, and tedious process, which is why it takes many years, and this is what's known as the uranium enrichment process. Now that we understand how enrichment works, we need to understand enrichment itself. Why does enrichment have different degrees and levels? The percentage of uranium-235 in the mixture, which is the enrichment level, needs to reach a specific number depending on the use. For example, if a country is enriching uranium to operate a nuclear power plant for electricity generation, in this case, it needs enrichment to reach a percentage ranging from 3 to 5%. However, if the goal is to conduct medical and scientific research, the required percentage is around 20% enrichment. If the goal is to build a weapon or a destructive bomb, the enrichment level needs to exceed 90%, what's known as highly enriched uranium or weapons-grade uranium. But there's an important point here. The effort and time required for enrichment aren't distributed evenly. In fact, raising the enrichment level to 20% takes about 90% of the time, effort, and energy required to reach a nuclear bomb. The remaining 70% takes much less time, because the amount of material being processed in this case is smaller, and the impurities are largely known. That is why, when a country reaches 20% enrichment, the international community becomes concerned, because this means the time remaining to reach the bomb stage is a matter of weeks or a few months. Of course, other factors can alter this time frame, such as infrastructure, the resources required to operate the facility, and secrecy, since many countries continue to do this in secret. And here the question arises, if we assume that a country has managed to overcome all these obstacles and has finally reached a 90% enriched uranium, does that mean that this country now has a nuclear weapon? The answer is definitely no. Enrichment is merely the provision of fissile raw material, and converting that material into a weapon is an entirely different matter that takes additional years of secret research and experimentation. Enriched uranium must be shaped and cast into a spherical mass. This sphere forms the core of the nuclear bomb, and handling it requires special facilities for radiation protection. Even more difficult is designing the detonation mechanism itself, because uranium doesn't explode like gunpowder. You can't just light a fire to make it explode. When uranium-235 reaches critical mass and a neutron strikes it, its nucleus splits, releasing this immense energy plus additional neutrons. These neutrons strike other atoms, triggering a chain of rapid explosive reactions. All of them must detonate at the exact same moment for the explosion to be a nuclear one. If we at the facts, we'll see that the US is the fastest country in history to have built a nuclear bomb. The Manhattan Project began in earnest in 1942, and they managed to achieve the first successful test explosion in July 1945, meaning it took them only 3 years. The reason they were able to achieve this speed was World War II, which provided an open-ended budget for the project and a massive industrial effort because the whole world was supporting them to defeat the Germans. The greatest minds in physics at the time were in America, even if they weren't originally from America. So it's not that America built the bomb, but rather that it was a collective effort by most of the world's nations, starting with Albert Einstein, who sent a letter to then US President Roosevelt, warning him of the Germans' plan to develop a nuclear weapon through Niels Bohr, one of the brightest scientists in the field, to Robert Oppenheimer, who was the project director, and Enrico Fermi, and many others. More than 130,000 people participated in the project with a budget of nearly $2 billion at the time. And even the Soviet Union, which entered the race shortly after them, was able to detonate a bomb about 6 years into work. But it is most likely that spies obtained sensitive information from the original Manhattan Project, meaning they weren't starting from scratch. Finally, there is one piece of information we need to clarify. Uranium-235 is not the only element used in the manufacture of nuclear weapons. There is a second element, plutonium-239. The difference is that plutonium is not AI. It is produced inside nuclear reactors themselves and extracted from uranium-238, which, as we mentioned, we don't use. The difference is that plutonium doesn't require enrichment in centrifuges, but only chemical separation. The problem is that separating it is very difficult and dangerous because its radiation is terrifyingly strong and requires advanced technology. In the Manhattan Project carried out in the US, they used both materials because they weren't yet sure which one would work. The little boy bomb dropped on Hiroshima was uranium, while the Fat Man bomb dropped on Nagasaki was plutonium. So that's it, and the ones who made it this far are the real friends in building this channel. Give us a like before you leave, so we know how many of you made it. And don't forget, if you have a question that pops into your head in the middle of the night and stumps you, write it in the comments below the video so we can answer it. Bye.